Welcome to Fuzzy Mathematics, the Basics. In the previous lectures, we have talked about Hesse diagrams, which are used to represent pulses, and we have talked about elements of pulses that have certain extremal properties. In this lecture, we are going to talk about a special type of pulses, lattices. A lattice is a partially ordered set in which every pair of elements has both a supremum and an infimum. Let's do an example. Example 1. Suppose X is the set with the three elements A, B, and C. We know that the power set of X together with the inclusion relation is a pole set, which is represented by the following Hesse diagram. Determine whether the pole set is a lattice. That is to determine whether every pair of elements has both a supremum and an infimum. What are the elements in the pole set represented by this Hesse diagram? It has 8 elements: the empty set, singleton A, singleton B, singleton C, set AB, set AC, set BC, and set ABC. If we try to check whether every pair of elements has both a supremum and an infimum, that would be a lot of work. We won't do that here. Do you remember the definition of a chain? A chain is a subset of a pole set, such that every 2 elements of the subset are comparable. So, every pair of elements in the same chain has both a supremum and an infimum. For example, the empty set is a subset of the singleton C, a subset of AC, a subset of ABC. This is a chain. Every pair of elements in this chain has both a supremum and an infimum. Another example, the empty set is a subset of the singleton C, a subset of BC, a subset of ABC. This is also a chain. Every pair of elements in this chain has both a supremum and an infimum. So, we only need to check the pairs of elements, not in the same chain. For instance, the singleton A and the singleton B, the supremum of these 2 sets is set AB, and the infimum of these 2 sets is the empty set. What about set AC and set BC? The supremum of these 2 sets is set ABC, and the infimum of these 2 sets is there are 2 lower bounds, the singleton C and the empty set. The infimum is the singleton C. What about the singleton A and the set BC? The supremum of these 2 sets is set ABC, and the infimum is the empty set. In this way, we can show that every pair of elements in this pole set has both a supremum and an infimum, so it is a lattice. This conclusion could be generalized. Suppose X is a set. The pole set of X together with the inclusion relation is a pole set. Determine whether this pole set is a lattice. We need to determine whether every pair of elements has both a supremum and an infimum. What are they if exist? That's a question worth pausing to consider. I think you could get the answer. We know that a lattice is a partially ordered set in which every pair of elements has both a supremum and an infimum. Next, we are going to talk about the algebraic structure on lattices, which is the main topic of the latter part of this lecture. An algebraic structure is also called an algebraic system, which consists of a set and one or more operations, usually satisfying some properties. Wait a minute, a lattice is a pole set, a partial ordered set. There exists a partial order, but no operation. In fact, there exist two binary operations in each lattice. Suppose L is a lattice. Every pair of elements in the lattice has both a supremum and an infimum. We can define two binary operations. First, we can define the join operation as follows. The value of this function at the ordered pair A, B is A join B, or the join of A and B, which is assigned the supremum of the pair. Likewise, we can define the meet operation as follows. The value of this function at the ordered pair A, B is A meet B, or the meet of A and B, which is assigned the infimum of the pair. A lattice is a poset in which every pair of elements has both a supremum and an infimum. The supremum is unique when it exists, and the infimum is also unique when it exists. So the two binary operations are well defined. The algebraic structure that consists of the lattice L and the two binary operations, the join and the meet, is called the algebraic structure induced by the lattice. And that's what we are going to talk about. Theorem 1. Suppose this is the algebraic structure induced by the lattice. Then the two binary operations satisfy the following properties. First, the idempotent laws. The join of A and A equals A. The meet of A and A equals A. Second, the commutative laws. The join of A and B equals the join of B and A. The meet of A and B equals the meet of B and A. By the definition of a lattice, we have that L together with the partial order is a poset. First, using the reflexivity of the partial order, we have A is less than or equal to A, so A is an upper bound of A and A. Considering that the supremum is the least upper bound, we have the supremum of A and A is less than or equal to A. But the supremum is also an upper bound, so A is less than or equal to the supremum of A and A. Using the antisymmetry of partial order, we conclude that the supremum of A and A is equal to A. That is, the join of A and A is A. Similarly, we can prove that the meet of A and A, which is the infimum of A and A, equals A. Next, we will prove the first equality of the commutative law. By the definition of join operation, we have the join of A and B equals the supremum of A and B. The join of B and A equals the supremum of B and A. Because a set is an unordered collection of elements, we have the supremum of A and B equals the supremum of B and A. The join of A and B equals the join of B and A. Similarly, we can prove that the meet of A and B equals the meet of B and A. This completes the proof. Now we have proved that the algebraic structure induced by the lattice obeys the idempotent laws and the commutative laws. That's the end of this lecture. Next time, we will talk about some of the other properties in this algebraic structure. Thank you.